All right, problem number 10 from group theory. We're going to do part A. This is a really fun problem. It says find the order of G given by all invertible matrices of the form this guy, where A and B are coming from the field of 7 integers, so like Z7, where the group operation is matrix multiplication. Okay, yeah. So we want to find the order of the invertible matrices of this form. Okay, we're going to think about the order as in the total possible number of elements. And for part A, we have such a matrix. So, okay, a matrix of the form. Okay, let me begin P matrix. Let's see, we have 1 and B, 0 and A, and P matrix. Okay, so a matrix of the form is invertible if and only if the determinant is non-zero. It's non-zero. Okay, and we can see that the determinant of this is just going to be A, because that's 0. And maybe I'll call this A. Okay, a matrix of the form, this guy, is invertible if and only if the determinant is non-zero. So observe that the determinant of A is equal to A, and A is non-zero. A is non-zero for, okay, so A is in F7, so there are 7 possibilities, but it can't be 0, so there's 6 possibilities. Observe that the determinant of A and is equal to A, hence there are 6 possible choices for A. The choice of B doesn't matter since this is 0 regardless of whatever you pick. And the choice of B can be any element from F7. Thus there are 6 times 7, which is 42 total elements of G. Hence the order of G is 42. Okay, this is part A. Now we want to do part B. So we're going to open a proof environment, part B. Okay, it says for each integer p that divides the order of G, find the number of CeLO p subgroups of G. Okay, so we know the order of G is equal to 42, which is equal to 2 times 3 times 7. Okay, so our CeLO subgroups are a CeLO 2 subgroup, a CeLO 3 subgroup, and a CeLO 7 subgroup. Okay, having done the problem, I know that starting with 7 is the easiest. By the CeLO theorems, the number of CeLO 7 subgroups, let's see, is congruent to 1 mod 7 and it divides 6. The only divisor of 6 that is congruent to 1 mod 7 is 1. Hence, the number of CeLO 7 subgroups is 1. Okay, that's the easiest one. Now we want to think about 3. Okay, so again, by the CeLO theorems, I'm just going to write N3 is congruent to 1 mod 3, and N3 divides, let's see, 14. So if we think about divisors of 14, there's 1, 2, 7, and 14. 14 is not congruent to 1 mod 3, 2 is not congruent to 1 mod 3. So the possible choices for n3 are 1 and 7, or 1 and 7. And we're going to rule out 1. So if there's one 3 CELO subgroup, then that CELO 3 subgroup is normal. Yes, then that CELO 3 subgroup is normal. This is what I want to contradict, essentially. So I want to think about what an element of order 3 of this form would look like. And it's easiest to think of if we consider when b is equal to, well, maybe I'll say this instead. So observe that 2 cubed is equal to 8, which is congruent to 1 mod 7. Okay, so consider, we're going to call this guy B, and I did not. I want to copy that matrix so I can easily adjust it. Okay. And I copied the whole thing. So we have B to be, if this was 0 and A was 2, so like that. So we consider this matrix, and so we observed that 2 cubed is equal to 8, which is congruent to 1 mod 7. So if we were to multiply this matrix by itself 3 times, what we'd do is we would just keep multiplying this 2 by itself, and 3 times would give us back to 1. So this would give us the identity. Consider this. Thus, b cubed would give me the identity matrix. Hence b has order 3. Therefore, the cyclic subgroup generated by B is a subgroup of order 3. Thus, it is a CELO 3 subgroup. Okay, and my contradiction is going to be that this is not normal, which, if there's only one 3 CELO subgroup, then it has to be normal. But remark that if we take, okay, this is where I just want the matrix. So if we take the matrix and we multiply it by this guy, and specifically we're conjugating it, so we're also going to multiply it by this guy's inverse. Doing the matrix multiplication out, one more thing, this is the inverse. So if you were to do the matrix multiplication out, I did the computation, and hopefully it's correct, you get this guy, but if we notice, B has this 0 in this corner, and this has a 1 in this corner. So if you operate B with itself, well, we know what it looks like. It's just this, but with 4. And then the next one would be the identity. So this is definitely not in the cyclic subgroup generated by B. Okay, remark that if we conjugated B by this, we get something that is, I'll just write it here, it's not in cyclic subgroup generated by B. Therefore, the CELO 3 subgroup is not normal. for this CeLO 3 subgroup is not normal. So, okay, hence the CeLO 3 subgroup, there are 7 CeLO 3 subgroups, because it could have been 1 or 7. We ruled out 1 because it had to be normal, but it's not normal, so it has to be 7. Okay, and lastly, we want to talk about the CeLO 2 subgroups, and I'm going to make a similar argument to what I do here, where I rule stuff out. Okay, so lastly, the CeLO 2 subgroups are congruent to 1 mod 2, and they divide, let's see, what do they divide? They divide 3 times 7, which is 21. Hence the possible number of CeLO 2 subgroups are, it could be pretty much any. It could be 1, 3, 7, or 20, or 21. Okay. And we want to show that it is 7. And actually I'm going to take this is a slightly different route. In this route, I'm going to show that there are 7 elements of order 2, and each one forms a kind of their own cyclic subgroup of order 2. Hence, there are 7 CeLO 2 subgroups. Okay. So we want to generate, arbitrary elements of G that have order 2. So we consider A operated with itself. So, okay, I want this to be B, and I want, oh, I didn't mean to touch that one first, but that's fine. It should be an A. And I want to do the same thing with this guy. B and A. So if we were to square A, I want to know when this gives me the identity matrix, because that would be an element of order 2. So doing the matrix multiplication out, and let's put this in math mode like that. This might go on to the next page, but okay. So doing the matrix multiplication out, let's see, this one's not terrible. We get definitely a 1 in this position. We get B plus AB, or BA, whatever. And the bottom, we definitely get 0 in that corner, and we get A squared. And because we want something of order 2, we want to know when this corner is 0 and when this guy is 1, because that would be the identity matrix. So we want B, I'm just going to factor that B out, B times A plus 1 to equal 1, and A squared to equal 0, sorry. This guy to equal 0, and this guy to equal 1. Okay. And we'll observe that if A is 1, then we get B 2B equals 0. And then if we think about the elements from F7, so let's write this out. If A equals 1, which is one solution for A squared equals 1, then 2B equals 0. Hence, B has to be 0. Because, for example, if B was 1, we'd have 2, which wouldn't work. If we'd have 2, we get 4, 3, we get 6, 4, we get 8, which is 1, 5, we get 10, which is 3, 6, we get 12, which is like 5 or something, definitely not 0. And that's all of them. So B equals 0 is the only possible choice. However, if then hence B equals 0, which corresponds to the identity matrix. Okay, so this corresponds to the identity matrix. Now we want to look at the other possibility. What else can we have from this guy? Well, 2 wouldn't work because 4 is not 1. 3 would be 9, which is 2. 4 is 16, which is not 1. 5 is 25, which is 4. 6 is 36, which is congruent to 1 mod 7. So if a equals 6, then a squared is equal to 36, which is congruent to 1 mod 7. So we have that 7b equals 0. Well, 7b, first of all, is just congruent to 0. So the choice of b can be any element. Hence, we can choose any element from F7 for b. And there are 7 elements from F7. Thus, there are 7 elements of G with order 2. Okay, we move down. Therefore, there are 7 CeLO 2 subgroups, which is the last CeLO subgroup that we wanted to talk about. So there are 7 CeLO 2 subgroups, there are 7 CeLO 3 subgroups, and there was 1 CeLO 7 subgroup. Really awesome and rich problem.